As we continue moving through section 11.6, we're just going to continue to get more practice applying the two different series tests. So here's problem number 4. We've got a whole term here, and this one is one of those problems that is almost begging us to apply the root test. That we said that, well, what kind of clues us in to use the root test? Well, this is one situation. When everything is being raised to the nth power exactly the way this is, the 1 over n power would then cancel. So this is a fairly easy limit to look at. So again, that's kind of the motivation here. That's what we're trying to identify. That was a really, really huge hint here. And this would be one, if you try to apply the ratio test, would be pretty much a nightmare. So let's first apply the root test. So I'm taking the limit, the absolute value, which does nothing here, but it's our first problem, so I want to make sure I include it. The absolute value of all of this to the nth power, and this is where, like I said on the original, whether you want to then write the nth root or all of that to the 1 over n power, but either of these are the same. I got to be honest with you. When people write the radical, some people forget about the n and they just treat it like it's a square root. So that's why for some reason, for some people I should say, they strongly prefer this. Okay, but now this is a problem like before. Oh, actually one quick thing to notice, it's just the nth term. There's no n plus 1 here, just taking the original a sub n, absolute value to the 1 over n. That's all there is to setting up this limit. And in this problem, well, the absolute value isn't doing anything. Even you might see this negative, but just think about it for a moment. Once you start plugging in 1, 2, 3, well, no, this still always ends up positive. So nothing bad there. Absolute value drops. And now taking the nth power to the 1 over n, well, some people just look at this like squaring a square root and it cancels. Other people look at it as combining properties of exponents. Power to a power you multiply. N times 1 over n is n over n, which simplifies. Whichever way we look at it, that is the simplification. That is what both the ratio and root test have in common. The ratio test, well, we want to do the whole setting up the n plus first term over the nth term, then cancel, then take the limit. Here, it's all about this 1 over n canceling here. Now, what's left behind? Well, still a limit. We've got some dominant terms to consider. Oop, not the n, right? The dominant term is just the n squared here and the 4n squared here. That limit is 1/4. That is less than 1. So our series converges, but this time by a root test. Okay, so just our first example. Nothing too bad, but this was a little bit of a nice example. And this one was, again, literally tailor-made for the root test. All this to the nth power was almost begging us to raise it to the 1 over n to make that simplification. Still having to take the limit, still making your conclusion. And I know sometimes it seems silly, everybody, but sometimes these little things, the less than 1, greater than 1, people undervalue that. That's a part of your proof. So don't forget to include that. Less than 1, greater than 1, that is what supports why you get your final answer. And again, both ratio and root, it's about being less than 1 or greater than 1. Both of them, less than 1 leads to converges, greater than 1 leads to diverges. Okay, so now let's jump right in to problem number 5. Problem number 5, let's look at minus 7 to the n power over 2 to the 3n power. This one is pretty interesting. Nothing's obvious here. I see that n exponent, but it's not all raised to the n the way this was. This n just applies here. But now some people might be a little clever and realize if you use your property of exponents right here, you can get this to be something to the nth power to then make that so perfectly clean. I'll show you an alternative in just a moment. Others might even really be clever, maybe not seeing it right exactly here, but maybe starting to have that influence. N is only an exponent here. So even though it's being used in both pieces, N as an exponent, this is a geometric piece. Here, this is also a geometric piece. There's no other pieces. This whole thing, believe it or not, is geometric. So maybe you might only realize that by actually writing out some terms, but that would be another alternative. I'll show you that at the very end. This is geometric. So just by finding the value of R, you can make your conclusion converges, diverges. But by seeing both of these here, it's not quite as perfect here, but by seeing N as an exponent, even though it's occurring in multiple places, that's another indicator to try a root test. So still taking that limit. Here I'm just going to go a tiny bit faster, just in the sense when I take the absolute value, that changes that -7 to a positive. So I get 7 to the n, 2 to the 3n, all to the 1 over n power. Again, everybody, just like the ratio test and just like we saw in the root test right here, don't take the limit right off the bat. If you're applying ratio or root, there's always some simplification before you really just jump in and take that limit. Here, the n and the 1 over n canceled. Similar here, but distribute it to both top and bottom. 7 to the n to the 1 over n is just a plain old 7. 2 to the 3n to the 1 over n becomes 2 cubed. There's not even any n's left. This is 7 over 8. The limit of 7 over 8 is 7 over 8. This is again less than 1. So once again, this converges by a root test. But now, just coming back over here, that's the little fancy part. Remember, AR to the n-1 power was our original geometric series, but if all we saw was stuff to the n power, it didn't have that perfect form, but all that stuff to the n power is R. This is not R because that stuff to the n power has more n's in it. But with this, just a little manipulating, 2 to the 3n is 2 cubed to the n. So I could bring all of that together, minus 7 to the n over 2 cubed to the n. 2 cubed is 8, can be grouped together as minus 7 over 8 to the n. You can still write out some terms if you prefer, but now R is minus 7/8. The absolute value of R is less than 1. Different reasoning, but we still ended up with the same result, and that result is fully supported by the work that we showed. So again, that's what we've also seen before. It's not always that every series has exactly one test that'll work with it. I mean, especially the comparison tests, we showed you could pretty much always use a limit comparison, but others, the regular comparison could help. So again, others, there's still other possibilities. So again, we've had a lot of little things come up. There's not always, some of these series have one test that works so well with them, but for others, there are some alternatives, but everything must be supported. And just a quick little fact, by the way, if you go through in the book and read a little bit more about the root and ratio test, both of these proofs the proofs have geometric series work in them. So it's not that surprising that this result worked out so similarly. Two different approaches, but that 7/8 was kind of the key in both pieces. But here we're looking at it as R. Here that just happened to be the limit value, the L that we got at the end. So again, few good problems here. Let's still play a little bit more. Let's stick with this one for one more moment. So one more moment. Minus 7 to the n, 2 to the 3n. Maybe you still just look at both of those and say those are both geometric components. Geometric components, even though it's not a combination of geometric and p-series, they're both geometric components. A ratio test still seems like a possibility here, and it's going to work very well. So let's apply a ratio test here. Absolute value makes that a positive, replacing n with n plus 1. Here I'm already distributing 3 quantity n plus 1 becomes 3n plus 3. That's the absolute value of a sub n plus 1 divided by the absolute value of a sub n. So the absolute value, again, that -7 became a positive, and dividing by the fraction, I already flipped and multiplied by the reciprocal. So there's a little second reason I'm showing you this problem in another form, just to again show you there's nothing wrong at all if you're comfortable just jumping to this point in the ratio test. Cleaning up, we've seen very similar things here. 7 to the n times 7, 7 to the n's cancel. 2 to the 3n times 2 cubed, the 2 to the 3n's cancel, and once again this limit is 7/8. There's that value again, still less than 1, so we still get converges, but this time we get that by ratio test. So again, in a lot of ways, that problem, what we started calling problem number 5, that series had a lot of flexibility to it. It fit a lot of different categories that we mentioned. And only as an exponent geometric series, and being able to write all that to the n power, a good possibility, a good situation for a root test. Having multiple geometric series components, a good possibility for a ratio test, all worked very well. Okay, now I want to go back, take another look at problem number 1. We had 3 to the 2n power, 5 to the n minus 1 power times n cubed. This one, go back and look at it in part 1 video. We already saw that as a combination of geometric and p-series, and we said ratio test was a good pick, was a good choice. And ratio test was not bad. Again, you can certainly go back and look through that again. But let me point out what happens here if you apply the root test. Some people, they see these n's as exponents and they get very excited for the root test and they really undervalue what happens here. So let's take a look. Limit, absolute value, well, everything's positive. Don't have to worry about. Nothing to worry about with absolute value. And again, the root test, so not using the n plus first term, just the original a sub n. As we say, before I think about the limit, think about cleaning some things up. And right off the bat, this piece, I mean, that's pretty nice. As we've seen similar things like this, 3 to the 2n to the 1 over n, the n's would cancel. You're left with 3 squared, 9. This, not quite so easy. You'd have to break this up. You'd have to think of this as 5 to the n times 5 to the negative 1. This first piece works like a charm. 5 to the n to the 1 over n gives me a 5. But this piece, this becomes times 5 to the negative 1 over n power. And then this last piece, and this is the worst piece, n cubed to the 1 over n becomes n to the 3 over n power. So several people would look and say, hey, what's wrong with this? Set up the root test, distributed this. Remember, this distribution only works because everything is attached by multiplication and division. Any addition, subtraction, you can't distribute exponents like that. But with only multiplication, division, distribute the exponent to everything, cleaned up a bunch along the way. Right here, there's an n. So as n goes to infinity, just this piece right here, well, minus 1 over infinity, that goes to 0. So the whole thing goes 5 to the 0 power, that goes to 1. So this whole thing is going to 1. That doesn't look so bad. But look at this mess right here. I'm going to need a little extra room, And I'm going to need to focus on that piece all by itself. This is not trivial at all. What you would get here is infinity to the 0 power, right? N goes to infinity, and then this is 3 over infinity, so like this. K over infinity goes to 0, but that's just the exponent, just like it did here. But 5 to the 0 was fine. Here we still have an n, and n is also going to infinity. So that's why I'm getting infinity to the 0. And if we remember, that's not so trivial. That is indeterminate. This is where I need the log. So I'd have to end up doing log of this whole thing. And then the log of all this, the 3 over n can kick out in front. Technically right here on this line, this piece is going to 0, 3 over infinity, but log of infinity goes to infinity. So I've changed from one bad indeterminate, well, not bad, there's nothing bad about it, but indeterminate form to another. But this one we're making good progress because I could easily make this 3 log n over n, which is now an infinity over an infinity. Have to change to x's to apply L'Hopital's rule. One over x over 1. And finally, that goes to 0. Well, if this piece goes to 0, that would be my log of y goes to 0. Therefore, y goes to the e to the 0, which equals 1. So not trivial at all. What happened to this piece? Look at all this extra work I had to do just for that one little component. But now finally we get that goes to 1 as well. This whole limit is 9/5 greater than 1. We once again diverge, but this time by the root test. Our series, just as I always say, I'm kind of putting it at the end with my conclusion. Some people go right back to the original problem. They can highlight this is what they mean by, they say, the series. Other people rewrite it. Any of that is fine, but ultimately we better get the same conclusion. We got this diverged when we did it using ratio test, and we still get the same result. But just a quick comparison, personally, I think this was a lot easier. Just a lot easier, cleaning up a little bit of exponents and not a bad limit, versus this. That limit was not trivial. Again, could you do it? You could, but realize how much went along with that. That's not just a quick and easy one. You got a lot of work to show that that does go to 1. Okay, everybody. Last problem for section 11.6. Getting some good practice. Again, certainly want to get through the homework in your textbook. I believe it's examples 4, 5, and 6 are all very good ones to consider. But now let's finish with this problem. I want to look at, this would be problem number 6. And we are looking at the summation of n to the n over n factorial. This will be our last problem. So now people see that n as an exponent, but that factorial, that really, really has to stand out. We did number 2 had a factorial, things cleaned up nicely, had a pretty easy ratio test. Just because the factorials there doesn't make it an easy ratio test, we saw in problem number 3, we started with multiple factorials, so we could clean up and not have a factorial in our general term, but that's not happening here. This does have the factorial. There's no other factorials for this to cancel with. So yes, this is going to be another ratio test problem. So ratio test, careful. This is by far the number one mistake. People don't replace all n's with n plus 1 here. They replace the convenient ones, but we don't get to do that. So replacing n with n plus 1, we get n plus 1 quantity to the n plus 1 power over quantity n plus 1 factorial, and then dividing by a sub n times the reciprocal. Technically, I had my absolute value again, but once again, there are no negative terms, So that just dropped without cleaning anything else. Okay, the factorials do clean up nicely. Expand the bigger one so that I can cancel. And now this is a place where a lot of people feel stuck. But notice we do get a little lucky here. Right now, these you can't do anything with them. But notice through a lucky coincidence, you have an extra n plus 1 here. So right here, let's still expand this. Let's think of this as n plus 1 to the n power times an extra n plus 1. Just like we did with 4 to the n plus 1, things like that, we just broke it into two pieces, and that just coincidentally allows me to clean that up a little more. But it still looks a little ugly. We still have n plus 1 to the n power over n to the n power. Still not an obvious limit. Infinity to the infinity over infinity to the infinity. Lots of infinities. You want to try doing L'Hopital's rule even after you switch to x's. The derivative of x plus 1 to the x power. You need logarithmic differentiation for that. So still feels like we're a little stuck here until we realize that this should look familiar. All of this is now raised to the nth power. Now, some people may think, hey, let's do a root test. You can't combine ratio and root tests. We're already in the middle of a ratio test, so you can't swap and now say, okay, now raise this to the 1 over n. But notice they both are to the n power. So that can become that. Does that look familiar? I hope it does. We've seen it a handful of times, and here we're seeing it again. This is E. That limit, that exact, if you break it down a little bit more, separate that n over n plus 1 over n all to the n power as n goes to infinity. That was our original definition of E, and we pointed out a little algebraic equivalent at a different point, at an earlier point. So hopefully you remember that, because without that, that's the move you'd have to make. Now you're getting 1 to the infinity power with that move. As n goes to infinity, dominant term here, that's 1, 1 to the infinity. You got to do a whole bunch of work like that, and you'll eventually end up getting the answer is E, but we've already pointed out that's certainly fine if you just memorize that limit. That is, I give you full permission for that. E is approximately 2.7, so that is greater than 1. So now we know that this series diverges by our ratio test. Okay, so that's the end of 11.6. Make sure you get some good practice, and 11.7 will give some strategy, mixing all these different tests together. What stands out? How do we know to apply? Hope we have good practice to know if we're getting a good result, that's great. Support your answer and be done. And if the test is not working correctly, move on. Know what your alternatives are, move on until you can get a result based off of one of our tests.